Okay, in this video we take a look at electric circuits. We're going to study both series and parallel circuits and compare and contrast those, and also look at how we might apply some of the equations that we've been developing to analyze these circuits. So let's go ahead and begin. Electric circuits. So a circuit, any path along which charges can flow, and remember, again, it's usually the electrons that can flow between the terminals of that voltage source, and simply that's because the electrons are fairly loosely held to the parent atoms and can be forced to move throughout that circuit rather easily. So a circuit, any path along which charges are able to flow between the terminals. Now, you need to have a complete circuit in order for you to be able to have an operating energy transfer. And the reason for that is that there needs to be a complete path for those charges to flow from both sides of that terminal. There can't be any openings or any gaps. Now, oftentimes we use a mechanical analogy to understand how circuits work. So it's a little easier to visualize what's happening here with a mechanical setup than it is for an electrical setup. But nonetheless, any kind of mechanical flow here is going to require some energy source. The energy source for a mechanical system would be this pump. And of course, that pump is probably plugged into some sort of electrical outlet here to be able to provide some electrical energy. But that pump is there to drive the water through the system. It's exerting that force necessary to be able to move that water. So over in the electrical circuit, that would be the voltage source, and that would be typically a battery if it's something that we'd be building in our classroom. If it's, of course, something that you plug into your wall outlets at home, that voltage source would be coming from the power company. But we need some way of sort of exerting that force on those charges. Now, a valve in a mechanical system would be there to either turn on or turn off the flow. Well, that would be a switch in an electrical circuit, and a switch looks something like that. Notice oftentimes the way that we would say a switch when a switch is closed. What that means is sort of opposite of what you think when a valve is closed. A valve being closed here would sort of shut off the water flow. When we say a switch is closed, that means that there's a complete path. So a closed switch would be more like an open valve, right? So the switch is closed means current can flow. Okay, so oftentimes students get confused there when you think about a mechanical valve being closed. That means it's shutting off the water. When we talk about closed switches, that means the charges can flow. Now, in most mechanical systems, there's always some sort of restriction that is sort of going to impede the flow of that water, maybe. And so a restriction in a mechanical system is very much like a resistor in our electrical circuits. And this would be the schematic symbol that we'd use to represent a resistor. Okay, so there we go. A little connection between a mechanical system and an electrical system. Okay, now let's go ahead and take a look at series versus parallel circuits. So circuits can be connected in two common ways. Of course, we could mix these as well, and some of the activities that you'll do in your lab work will be a mixture of both series and parallel. But let's go ahead and take a look at these in detail. A series circuit forms a single pathway for the electrons to flow between the terminals of the battery, the generator, or the wall outlet. So a series circuit, if we were to build one in a lab, it would look something like this, and this is what the electrical schematic would look like. Okay. A parallel circuit forms branches, each of which has a separate path for the flow of those electrons. And again, a visual of what you would build in the classroom versus an electrical schematic along with what those devices would actually look like if we could draw them on the sheet of paper. Okay, so series and parallel, we're going to spend a little bit of time looking at these in more detail. Let's go ahead and do that here. So a series circuit, 5 things for us to look at, along with some graphs and some pictures to analyze. So a little bit more detail here. A single pathway for current, if one device fails, such as a light bulb burns out, everything else turns off. And recently, often about this time of year, people are putting up trees and they're putting lights on those trees. And all of those lights that you might put on like a holiday Christmas tree, often those lights are wired in series. And if one of those bulbs burns out, then the entire strand goes out as well. And it's simply because all the current flows through each particular device. Okay? So the total resistance is the sum of the individual resistances. Let's go ahead and add some of those numbers up here. Let's say that I have a 30-volt battery. So that battery is able to provide a potential difference of 30 volts between those two terminals. And let's say that each one of these light bulbs is operating with a resistance of about 10 ohms. And so if I connect all three of them up together like this, that would be equivalent to a single light bulb that is going through something like looks like this. Here, a single light bulb that has a resistance of 30 ohms. So the sum of the resistance of those would be would be 30 ohms because of all that charge having flowed through each one of those light bulbs. Okay? So we might say that that is the total resistance. It's just the sum of the individual resistances of each component. Now, current is equal to the voltage source divided by the total resistance. So if I have 3 light bulbs, each of them operating with 10 ohms of resistance, the total would be 30 ohms. If I want to determine the current being delivered when this switch is closed, thank you. If I want to determine that current, I would just use the I is equal to delta V over R, and I'm going to use delta V from the battery divided by the total resistance. So if I have 30 volts, and I'm putting that through a resistance of 30 ohms, I would just get 1 ampere of current flow. Right? So that would be the current through that circuit. Now the total voltage is divided across the individual devices. The sum of all of those voltage drops is equal to the supply. So if we were to take a look at what happens to the voltage, the potential in the line at the various locations along here, I know that this side is at a 30 volt potential relative to here. And so if I go through this entire thing, I see that this is at 30 volts relative to the ground. Well, I'm going to be dropping a delta V across each one of these things. Since each of these are exactly the same, I'm going to drop about 10 volts of potential across here. So this would be down to 20 volts. This would be down to 10 volts. And sure enough, when I get all the way down to here, I'm going to be back down to 0. So what I get is a delta V that in this case would be the same across each device, and they would add all up to the total voltage being supplied by that battery. Okay? So the total voltage is divided across the individual devices. The sum of all those voltage drops equals the supply. Now the voltage drop across each device is in proportion to its resistance. Now that's fairly easy to understand here. Since all of these resistances are the same, we would get the exact same delta V across each device because they all have the same resistance. They all impede the flow the same amount. Well, let's consider this picture over here where I have a 12 volt battery going through 2 circuit elements that are in series. One is 400 ohms, the other is 290 ohms. These no longer have the same resistances, so they're going to have different voltage drops across those. Now you can see this graph here showing the potential as a function of position is showing you what's happening at these various spots here. So let's go ahead and see. Letter D is at 0, and then letter E is at 12 volts, and that's because the battery is supplying that voltage increase as I go from one side of the terminal to the other. So that point is at 12 volts. Now, as I go through, there's no drop across from E to A because that's a very little resistance in that wire. So that is effectively at the same voltage as letter E. Now, I have a 7 volt drop across here, and I want to show you how we might be able to find that. Delta V is no longer going to be equally divided amongst these two because they have different resistances. So let's go ahead and see if we can't go through and figure out how to determine where that 7 volts came from. Now, I could do this in a number of ways. I could say that the current through this circuit is equal to the delta V of the battery divided by the total resistance, right? So I could certainly go through and do it that way. I could say that I have a 12 volt supply and the total is 690 ohms. So I could certainly go through and do that calculation this way, that the current flowing through there would be 12 divided by 690. That would be 0.0174 amps. So I know the current flowing through this thing is 0.0174 amps. So if I want to determine delta V there, I could say the current flowing through there, 0.0174 amps, multiplied by its resistance would be that voltage drop. So if I just take that number, multiply that by 400, I get 6.96 volts. So that would be delta V across here. Delta V about 7 volts. And that's between those 2 points. So if this was at 12 volts of potential, this one would be down to about 5 volts of potential. Now, how do I get that delta V there? I could do the exact same thing. I could look at delta V here is also equal to I times R. Notice it's got the exact same current, 0.0174 amps, but the resistance that current is flowing through is 290 ohms. And so when I multiply those together, I get about 5 volts. Okay? And so that's showing us how we would get the various voltage drops across those devices. Now, there is another way for me to do that, and I'm just going to show you just another way to do it using a little bit of proportional reasoning. I can say that delta V across that first resistor, so delta V across the 400 ohms, would be in proportion to that resistance based on this here. So I could say that it's going to be equal to the 12 volts that the battery is supplying, and then multiply that by how big of a proportion that resistance is to the whole. So that'd be 400 ohms divided by the total, which is 690 ohms. So that 490 or that 400 ohms is that percentage, if you will, of the total. So when we go through and just do that proportion, we see that that's a delta V of about 7 volts. I could also say delta V across the 290 would be the potential difference for the entire circuit divided by, or then multiplied by the 290 over 690. And again, this just represents how much of a percentage that resistance is of the whole. So a couple of ways to be able to do that. Either way is certainly fine. Let's go ahead and take a look at parallel circuits. Now, parallel circuits, the voltage across each device is now the same. So when I set this up, when I look at series circuits, we said that the current through each device is the same. Here, the voltage drop across each is the same. And that's simply because of the way it's wired. You notice that both sides of these light bulbs, no matter where I look, both sides of those light bulbs are connected to the same voltage source. So now they all have the same voltage drop across it. The total current from the source is now divided amongst the branches. So if I have some current flowing through here, on that I, we're going to get a certain amount of current flowing through each one of these things. And so if this is the current from the source, that's now going to be split up amongst these different branches. Of course, if it's being open, it's not going to have any current flowing through there, but you can see that that current is sort of divided up very much the way you might think of a river flowing with some water. If we have multiple paths for that water to flow through this river, you would see that this water then is going to be split up so that some goes one way and some goes the other way. And very much like we have here, since we have multiple paths for that to flow. The total current from the source is divided among the branches. The total current in the circuit equals the sum of the currents in each branch. So you could look at this and say, if I add up that current, if this is 5 GPM flowing through there, and this is 7 GPM, then I must have 12 GPM coming in through here. So we can sort of look at that as a mechanical analogy. If one device fails, all the other devices still work. So if somewhere we have a big clog here, a dam, we still get 7 GPM flowing through here. And so that would change the overall flow rate. If I lose that particular branch, I still have the other one operating. Here's a nice little mechanical analogy. Again, just said another way. I think this does the same purpose. Okay, let's go ahead and now take a look at parallel circuits and overloading. So your homes are wired in parallel, and so you might already know this. If you burn out a light bulb in your kitchen, that doesn't make every other light bulb in your kitchen or in your bathroom turn off, and that's because you have multiple pathways for that current to flow. As more and more devices are connected to a circuit, there's more current that's moving through the line wires. So the line wires are these things here. These are the individual circuits that feed the various homes, maybe in various rooms in your home. And so typically you have multiple branches across this from the line wires so that you can plug a variety of things into different wall outlets. When the current is excessive, overheating can result. When I add more devices on here, if I have something else in here like maybe a TV or Over here we have a strand of Christmas tree lights or whatever the case is. The more I add to there, the more current I have being drawn from our power supply. And if I overload it, that's when we could have potential fire hazard. Safety fuses are there to sort of shut things down in the event that you overload that circuit. So these are wires that will melt when the given current is exceeded, and they are connected in series along with the supply lines to prevent overloading. So the current actually flows right through this device, and this is a picture of what a fuse would look like for home wiring. These have been replaced by circuit breakers in modern buildings, and that's primarily because of ease of use and also the cost associated with replacing these things. So a circuit breaker is an automatic switch that turns off when the current is excessive. It looks something like this here. If you've ever seen one of these things, often they're in a lighting panel in the basement of homes or something. You'll see a little orange tab that's on here that when that breaker trips, you'll see like an orange or a reddish tab that shows that that circuit has exceeded the maximum allowable circuit, and then you just go through and reset that. Now, if you have to reset it and it keeps tripping, then something's wrong with maybe an individual component that you have plugged in, or there's something wrong, maybe a short that this is going to ground or something in the home. And so sometimes this happens, and then you have to actually go through and rewire that portion. It can be somewhat of a difficult job to do that. Okay, and let's finish this up by looking at a couple of examples. Here we have light bulbs in the figure, and this light bulb and this figure are identical. In one case, I have two light bulbs that are connected in series to a battery, and in another case, I have two light bulbs connected in parallel to a battery. In which configuration would you say more light is produced? And this is meant to be a concept-based question. A little bit more difficult to do if you're watching a video on this. Normally I'd pause and have you respond, talk with your other partner, or type something into the chat. But what do you think? And hopefully you see that more light would be generated over here. And the reason for that is that each one of these light bulbs are connected to the battery source directly. And so each of these things is going to get the entire voltage from that battery. And if this is 12 volts, I'm going to get 12 volts across here. And I'm going to get 12 volts across this because of the way that they're connected. Now, when I do this here, if this is a 12 volt battery, I'm going to get only 6 volts across this and 6 volts across that. So I have a much smaller delta V across each one of these things here. These things are going to glow very, very dimly here. As a matter of fact, if I added another path here, if I had another light bulb through here, then this would also get a delta V of 12 volts, and that would be really bright as well, just as bright as these others. If I added another light bulb in here, let's put that right over here. Now, these would each go down to 4 volts, and so these would be even dimmer still. And so now you can see that every time I add something to a series circuit, it becomes dimmer. Each one becomes dimmer as well. So obviously some problems with the series setup. Now, which do you think your headlights on your car are wired which way? And hopefully you realize that your headlights are wired this way. You can burn out one bulb. I often see cars that have one bulb burned out. The other one is still operating. They are wired in parallel for that reason. So there we go. Now, to finish up this video, this is a little bit more complex of a circuit. And instead of going through and trying to answer these things in this video, it often takes some back and forth to be able to fully understand that. So I'm going to save that discussion for us in a live setting or in class, and recognize that this particular circuit is one that I'm going to have you build on a circuit simulation that is a part of the lesson to put to practical use the things that we're learning in this video. So there we go. That completes the video on series and parallel circuits. Hope you found it helpful.